All right, welcome to The Explainer. Today, we're going to lay the groundwork for one of the most popular, most rock-solid programming languages on the planet, Java. We're going to break down all the essential concepts, from the ground up, so you can really see how it all clicks together.
So here's our plan for today. We'll start with the big question. What is Java? Then we'll get into your first building blocks, some recipes for code, the actual blueprint of Java, and finally, we'll cover its guiding principles. Let's get started. Okay, Section 1. What is Java? Let's really get a handle on the foundation here. Before we build anything, right, we have to know what our materials are. So, what exactly is this thing we call Java? Okay, so that's the official kind of textbook definition. I know, it's a mouthful, but let's just chop it up. Put simply, Java is just a really powerful, super flexible way to tell a computer what you want it to do. Now, there are a couple of key bits in there to hang on to. Object-oriented, don't worry, we'll get to that later, and few implementation dependencies. That second part, well, that's where Java's real magic starts to shine. And this leads us straight to Java's, well, its core superpower, this idea of write once, run anywhere. It's a game-changing philosophy. See, you write your program just one time. Then, this amazing little thing called the Java Virtual Machine, or JVM for short, steps in. Think of the JVM as a universal translator. It takes your code and makes it understandable to whatever device it's on. So your code isn't locked into a Mac or a PC or a specific phone. Nope. If the device has a JVM, your code just works. And that is the big takeaway right there. You have to remember, back in the day, we're talking the mid-90s, this was absolutely revolutionary. I mean, programmers were stuck rewriting their code for every single different computer. Java's universal nature just blew all that away. It's a massive reason why Java is still everywhere today. It's all about that promise of total flexibility.
All right, let's get our hands on the first set of materials. Time to look at the building blocks, variables, and data. We've got our language, now we need the bricks and mortar to actually build something. And in programming, that always starts with data.
So the most basic, most fundamental building block you'll ever use is a variable. The best way to think about it? It's just a labeled box. That's it. A box in the computer's memory where you can stash some information. You give the box a name, maybe player score or username, and then you pop a value inside it, like the number 100 or the name Alex.
Exactly. This is the simplest way to remember it. The variable isn't the actual piece of data. It's just the container for the data. And why is that so useful? Well, it means you can easily find that box later, grab the info inside, and use it in your program. Super simple, super powerful.
Now, these containers, these variables, they don't just hold one kind of thing. They come in different flavors, which really fall into two big categories. First, you've got your primitive types. Think of these as the Lego bricks. They're the simplest, most basic values you can have. Things like numbers, single letters, or a straight-up true or false. Then you have object types. These are more like the complex things you build with the Lego bricks. They're more complex structures, like a whole piece of text, which is really just a bunch of those single-letter primitives all strung together.
Okay, so we've got our building blocks. Our data is all nicely stored away in variables. But now what? I mean, what do we actually want to do with all that data? That brings us to our next section, recipes for code, or what programmers call methods and logic.
A method is basically just a recipe. Seriously, think of it like a recipe in a cookbook. It's a neat little block of instructions that does one very specific task. Maybe you have a recipe called bake a cake, or in code, calculate total. The instructions are all there, but they just sit on the page, right? They don't do anything until you actually decide to follow the recipe, or in programming, until you call the method's name and tell it to run.
And the whole point of this, it's all about being efficient. It's about being smart, not just working hard. Once you've written that recipe for, say, calculating a discount, you can use it over and over and over again, anywhere in your program. You never have to write those steps out a second time. It's the classic programming mantra, write it once, use it 1,000 times.
But wait, what if our recipes need to be a little smarter? What if they need to make decisions? That's where conditional logic comes into play. It's like a fork in the road for your code. It lets your program ask a simple question, like, is the player's score greater than 100? If the answer is yes or true, it goes down one path. If the answer is no, false, it goes down a completely different one. This is how programs stop being dumb instruction followers and start becoming dynamic and, well, intelligent. Okay, now we get to the big one, the architectural heart of Java. We've got our materials, the variables. We've got our instructions, the methods.
But how do we organize it all so it doesn't just become a giant mess? This is where we see the real blueprint of Java come to life, classes and objects. This is where object-oriented programming really kicks in.
So, in Java, pretty much everything revolves around this concept of a class. A class is just a blueprint, a template. It doesn't do anything on its own. It just describes what something is supposed to be like. For example, you could create a dog class. That blueprint would say, all dogs have properties like a name and a breed, and they have actions or methods they can do, like bark or wagtail. The class itself isn't a dog. It's just the idea of a dog.
And this, right here, is probably the most important concept in all of Java. If you remember one thing about how Java is structured, remember this. The class is the blueprint. Every single thing that actually exists and does stuff in your program is built from one of these blueprints.
So if the class is the blueprint, then an object is the real thing you build from that blueprint. Let's go back to our dog class. Using that blueprint, I could create an object, my dog Fido, who is a golden retriever. And you could create another object, your dog Sparky, who is a poodle. They're both dogs built from the same blueprint, but they are totally separate individual things with their own specific data.
That's really the simplest way to put it. The class is the idea, the concept. The object is the real, tangible thing. The class is the abstract theory. The object is the concrete thing you can actually use and interact with in your code.
Okay, last section. Let's zoom out and look at the big picture. The guiding principles that make this whole blueprint approach so darn powerful. These are kind of the rules of the road for object-oriented programming, often just called OOP.
There are three main ideas here that make OOP work so well. First, encapsulation. It's a fancy word, but it just means bundling the data and the methods that work on that data together in one neat little package, the object. It's like a TV remote. You don't need to know how the circuits work inside. You just press the volume up button. It keeps things simple and safe. Second, inheritance. This is all about not reinventing the wheel. You can create a new class that's based on an old one. So you could have a poodle class that inherits all the basic dog stuff, but then adds its own unique things. And third, polymorphism. Another big word, but it just means many forms. It's the idea that you can have one command, like speak, and a dog object will bark, a cat object will meow, and a duck object will quack. Same action, different behaviors. It's incredibly flexible.
And when you put it all together, that's the whole point. OOP isn't just a bunch of academic rules. It's a system for taming chaos. It's a proven way to organize really complex programs. By thinking in terms of these self-contained blueprints and objects, it becomes way easier to build huge applications and, more importantly, to maintain and expand them later on without everything falling apart.
So there you have it. We've gone all the way from the tiniest building block, a single variable, right up to the grand architectural philosophy of object-oriented design. We've laid the entire foundation, piece by piece. You've got the blueprints now. The only question left is, what are you going to build?